So velocity is the frequency times the wavelength. Okay, now let's look at this equation in particular using a light wave. So our light is a wave, and we're just going to call it E now. So instead of U, we're calling it E, and it's the second derivative of the electromagnetic wave with respect to distance equals 1 over c squared, second derivative of the electromagnetic wave over time squared. Now what this means is that we have a wave that is going to be a sine wave, as we just drew it out, in both space and time. Now it could arbitrarily be either a sine wave or a cosine wave. It doesn't matter which one, or it could be any arbitrary phase of one of those. So our most general form of this is going to be a plane wave, and that's a plane wave with respect to distance x and time t. So if we work that out, we can see that those are going to equal each other. If I take the derivative of an exponential, I get an exponential. So dE dx is going to be derivative of the inside k, and then there's an I, times E naught e to the I k x minus omega t. My second derivative, I now have I times I, so that's -1. K times k is k squared. And you see I get just the negative of the original expression back again. I'll get the same thing if I do it with respect to t. Okay, then we can just work that one out a little bit by just plugging in that solution there. Oops. So now I'm just going to plug in what my solution is, and I will have this derivative here, minus 1 over c squared, and then this derivative here, E naught e to the I minus k minus omega t equals 0. You can work that out further, actually taking the derivatives, and all that you're going to get is that our verification of what c is. And then times this guy. And this is just our justification of why we can say that c is the speed of light. And what we have there is that k squared equals omega squared over c squared. This is probably the form that you saw it in if you took physics before, although I find a lot of my students get confused over that. That's a Greek nu. It is more common to use that for frequency than F. So this is just saying that c equals lambda times velocity. Okay, now it is much more common for us to use momentum, especially in quantum mechanics, we're going to be using momentum instead of position. So we are going to have like our de Broglie wavelength, or de Broglie, I'm not sure how to pronounce that, where we have a relationship between the momentum and the wavelength. So if we wanted to solve for the wavelength, that would be Planck's constant divided by momentum. We don't much care about that. We don't care about solving for the wavelength. We just want to put everything in terms of momentum. And then also, because we don't really want to deal with H, we probably just want to use H bar instead, but I guess they just used H. No, H bar. I was going to say H bar is easier. So that would be H bar times 2 pi over the wavelength is the momentum. And then, as we saw before, we know that K is 2 pi over the wavelength. So we are going to go ahead and put that in here. Instead of the wavelength, we are going to have that wavelength is 2 pi over K. So our momentum is just going to be H bar times K. That's our most useful determination of that. And then we can write K as momentum over H bar. Okay, we're also going to be using energy of a photon. Said before is H bar omega. It's the only way I can ever keep those guys straight. So now in our equation we have d dx squared minus 1c. We're going to be looking at this line. And now, instead of writing e to the I k x, I'm going to be using this instead of k. So instead of k, I want to say that it is p over h bar. So I have p over h bar x, and then instead of omega, I would like to have e over h bar times t. I can factor out that h bar pretty easily, and then if I just go ahead and take those derivatives, I am going to get the second derivative with respect to x of this guy. So I have an E naught, which we will have in both of them, so we're going to keep that factored out. I will have E naught, I will have an I squared, because I'm taking the second derivative, I squared. I will have over h bar squared, and I'm going to have p squared minus over c squared. I am also going to have that h bar squared. I'm going to have an I squared, and it's going to be e squared. And then we have this whole chunk again. I over h bar px minus et. That all equals 0. So I can multiply my original function on both sides of the equation and it comes right back out. So what I get is I squared p squared h bar squared minus I squared energy squared over c squared h squared equals 0. Now these are going to cancel, these are going to cancel, cancel, cancel. And what we're going to get is that p squared minus e squared over c squared equals 0, or momentum squared equals energy squared over speed of light squared. Or just that energy is the energy of a photon, so that's the energy for a massless particle. Now you notice this is the relativistic energy, and where we would have like our relativistic total energy be components of momentum times the speed of light and rest energy. All throughout the Griffiths book and most of our applications, we're going to be considering that the velocity of anything is much, much smaller than c. So that's the only way that we can really make these assumptions here. Now this one is making the assumption that the rest energy is 0, or it's something that is massless. So that's just using Pythagorean theorem there. So just assuming that it is like a light particle. But now we're going to assume that this is the more exact solution, and then we're going to plug it back in to this form here. So that form, I'm going to go ahead and I'm going to factor out that I squared, which is -1, over h bar squared equals p squared minus e squared over c squared, and then times, I'm just going to call it e because I'm getting a little tired of writing out this whole thing. Oops, that's just I over h bar px minus et. And that all equals 0. Now, instead of this epsilon here, I'm going to replace it with my relativistic term. So I have -1 over h bar, and then that's going to be p squared minus e squared c squared plus m squared c4 over c squared times e and now we're going to, before I write my equal sign, we're going to assume that everything has to be, in order to justify this, what we're going to say is that not only do I have my energy, my electromagnetic wave from energy, I'm going to say that it is wrapped up into a generalized wave equation. So I have E equals E naught it's just some constant, times this plane wave. Now we're going to say that we have this wave equation. So this is like our just generalized wave equation. And we know that it has to satisfy the same particular criterion that we just went through. So I'm just going to call it some wave equation there, and then that can be multiplied by our E, and we could just keep it as E. We could write out the whole plane wave like they did here. They did drop the constant, but that's fine. But it's still just there. So it's just the same exact thing, except we kind of assumed that at this step we were able to think of it as being like the homogeneous solution. So this was the solution when the mass is equal to 0. Now we want to have the solution for when the mass is not equal to 0 anymore. And then we're going to also introduce the wave equation, saying like, or their wave function, and we have that multiplied on both sides of our equation. So we're thinking about it in terms of the wave equation now. And our wave equation is going to have to satisfy this sort of format. So we need to have this guy right here. So our wave function still has to meet all of these conditions. Okay, then we could just work out this derivative. Like, now we're going backwards. So before we looked at the derivative, and then that's how we got the constants out. Now we're going to go backwards, and we have our constants, but we want to see how we get those in terms of our derivative. So actually now I see how it would have been more useful to have that other guy out. So let's just write it out with our actual exponential there. Now I could, I suppose, do what they did and like wrap up that E naught term into the psi naught term, but I'm just going to keep it out there. Okay, so now let's go backwards and reconstruct our derivatives. So our first one, I guess you could even think of, you could, I suppose, actually even integrate each term, but I just think about it as if I wanted to, if I took the second derivative, what would get me p squared? Negative p squared over h bar squared. So that would be the second derivative with respect to x. So if I took the derivative with respect to x, I would get p times I over h. I do it again, I get I squared p squared over h squared, which will give me p over h, negative p over h squared. My second one, I know exactly where this one came from too, because this is something that we did before. So I would have my 1 over c squared, of course, because that just stayed out there. And then that one is going to be omega squared. Oh, whoops. I mean energy squared. Would be the second derivative with respect to time. That's how I could get that term out there. This term is not inside the exponential, so that one is not associated with a derivative. And then if we had the 1 over h squared outside, then I have to account for that being inside there. So it might be a little bit more useful to write that out like this. And then that'd be h squared, and then that'd be h bar squared. And then that's going to be times our wave function, psi e naught, which I suppose is not that important. We could have just had it lying out there. That was not omega squared. That was, there we go, et. And all of that equals 0. Okay, we know that we have to have certain conditions that our wave function has to meet. This is mostly lined out in the first few chapters of Griffiths, and this is what Schrödinger spent a lot of his time on the original paper on. So on his original paper, he approached it through the expectation values. It's just written kind of in different notation, unfortunately. But looking at an expectation value as being something that is determined by integrating the complex conjugate of the wave function times the wave function. And that's how you could get any expectation value for either position or for space. But it still has to be a wave, meaning that it has to actually satisfy this basic condition right here, which is what we spent the first part going over. So our wave function has to have that condition. It also has to be something that is existing in space, meaning that if we have a particle with such a wave function psi, then our probability of finding it anywhere between infinity, negative infinity and infinity has to be 100%. So if our particle exists, it has to be somewhere. So if we integrated the complex conjugate of the wave function times the wave function over infinite space, we would have a 100% chance of finding our particle there. The rest of this is pretty much just in different notation. Pretty much did the crux of it right here. Now we're just going to put it into a more familiar format. And one more approximation is going to be done, which is, again, that approximation that's always done throughout the entirety of Griffiths, which is we're not assuming relativistic motion here. Even though we're using relativistic energy at the moment, we are going to take an approximation to take that out. Okay, so just multiplying this guy through here, they went to del's to generalize into 3D space. I'm going to keep it just as x. So we have dx minus, and now we have, so just multiplying. So now I have this term. I'm dropping this guy. So this guy, we just, multiplied that on both sides. So this guy goes away completely. Now that would be minus this term here. We have 1 over c squared, del squared, psi, del t squared, minus now this term. That's m squared, c squared, So you see this originally had a c squared under it and was c to the fourth, so those canceled out there. Over h bar squared times psi, all of that equals 0. Now we're just gonna move some stuff around. So I would like to have it in my more familiar format, which is going to be this guy. So I have my second derivative with respect to space minus m squared c squared over h bar squared psi equals my second derivative with respect to time. So we're getting there, but we're not there yet. We have a second derivative, we have a second derivative, and we just have our wave function out there. Now we're gonna do our next approximation. So we had this was our energy plus m squared c to the fourth. I'm going to factor out this rest mass, or rest energy, mc squared. So what I get is energy equals mc squared plus 1 minus p squared m squared c squared, which you might recognize as gamma, or 1 over gamma, because that'd be 1 minus v squared over c squared. Now, because we are assuming that the velocity is a lot smaller, so that means that p is going to be smaller than mc squared, pc. Or we could say p is much smaller than mass times c. So now we're just gonna do that approximation here. Pull this guy outside of the square root. And say that's going to be, oops, there we go, roughly equal to mc squared plus p squared over 2m, which is roughly mc squared plus the kinetic energy T. So meaning if we go back to our wave function here, we said that it has to follow those conditions. We had our wave function was up here, psi naught times e to the I over h bar times p minus et. Now we're going to rewrite that with our new expression for e, our approximation. And then what we get is px. Instead of e times t, I now have mc squared times t. Oops, little t, not big T, little t. And then we have big T, kinetic energy, times little t. We could also write kinetic energy in probably a more general form. It's just the same as our classical kinetic energy So it's that 1/2 mv squared, or you could also write it in terms of momentum, so you get p squared over 2m. Okay, then we can now, the only thing we're doing here is let's just pull out that rest energy. And kinetic energy times time. Okay, now we have our wave function into that form. All that they did here was simplify it a little bit to just give it a different symbol. So here, if we take that function psi, and I take the first derivative with respect to psi, then I am just going to get I forgot the t. There we go. So what I'm going to get there is I am going to get derivatives of the inside. So I have this with respect to t, and then this is also going to be with respect to t. So I will have a negative I h bar mc squared times e to the negative I over h bar mc squared t, and then we're going to have this psi naught e to the I over h px minus t t, and then we will have the derivative of that. So d dt of psi naught e to the I over h px minus t. We take the second derivative, so let's take the derivative of the derivative we just took. We get this guy, this is our rest energy over Planck's constant squared, e to the negative I over h bar mc squared t times psi naught e I h bar px minus t, big T, little t. Then we have 2I h bar mc squared e to the negative I h bar mc squared little t. Then we have the partial derivative, or I guess we have the whole derivative, yeah, like we had before, of this guy. I'm running out of space. I h bar px minus t t, and then plus this. So it's just using the chain rule to get this whole thing out here. And then we have the second derivative. And we will just try to scrunch it in as best we can here. That's probably why they went ahead and just shortened it up there. Okay. Now what we have here, or we can make our approximation, is that this first term is big and this second one is little. So we're not really going to worry about the second part. So we're not going to worry about the second part at all. We're just only going to worry about the first part, because we are assuming that the velocity is much, much smaller than relativistic velocities. Then what they did here was they used this idea that these two terms, so this term here, the second derivative, and then this guy up here, 2I times mass over h bar times the second derivative of this whole thing, e to the I over h bar equals 0. So now we can simplify this a lot. So it's just by using the fact that this term is small, it's not going to be important in our equation at all. So we can go ahead and we can discard that. And then just looking at the relationship between our first two terms, and you can go ahead and look at this. So using, this approximation here, and they did include the reference, which is in the back of the paper for the justification for that guy. I believe, it's hard for me to see, I think that is 13. Though I can't tell you if that one in particular is in English or not. We can then make this approximation. This is just an approximation though. We can multiply both sides by this term. That's going to go away. We will now have this second derivative of that wave function. So my second derivative of my wave function, which I am going to go back to my original and just say that that is psi now. So second derivative with respect to space of psi plus 2 times I times m over h of the first derivative with respect to time equals 0. Now we can work that out, that we would have the second derivative of that guy with respect to space would give us I squared p squared over h bar squared plus the first derivative with respect to time. So we have 2 times I M E. We will have another I come out, and we will have an H bar come out, and we had an H bar on the bottom. And then psi naught e to the I H bar px over e equals 0. And then we could get that I squared p squared h bar squared minus 2i, no, we'll just do squared e h bar squared equals 0. Cancel, 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 cancel. And what we have here is just kinetic energy. Right? So that's E equals so that's just our kinetic energy term there. So we went from relativistic energy of a massless particle with zero rest energy to our energy. All these approximations, all they really did was take our energy down to just be the kinetic energy term. Oh, I think I was even calling it, I think I had even just done that before where I just called it T. So it's just our classical kinetic energy term. T. There we go. So it's just our way of checking to see if this is okay or not. And it checks out that this is okay. Now you'll notice that we only have kinetic energy. We don't have potential energy. And that's what's missing in our, yeah. Oops. So I'm going to go back up a line, up to there. 2im h bar d psi dt, and that equals 0. We can rearrange that a little bit. So I could have negative. So I'm going to subtract this on both sides. And then I can move some stuff around. Oh, that is squared. Squared. Because we had the h on the bottom there. And we got the h out from the top. So we got h out there when we took the first derivative. Okay. And that is squared too. No, that one is not squared. No, there we go. I had it right the first time. It was just h bar. Okay. And then we can just rearrange that a little bit to get the familiar form. Except you'll notice we do not have potential energy. So we don't have our potential energy in there. We can multiply both sides by h squared, because we want to have h squared there. I'm going to divide both sides by m and divide by m. So now I'm going to have that out there. This one is going to cancel. So I have negative, oh yeah, let's divide both sides by 2 as well. So I have negative h bar squared over 2m times del squared, oops, times psi x squared, those canceled out, equals I times h bar times d psi dt. And my potential energy in this case is 0, but it's a little bit of an explanation for where that comes from. So hopefully that was helpful to somebody.